Okay, testing, checking to see if checking to see if this works. Okay, hello class. This is Mr. Burt coming from you from the internet, from beyond the towers and satellites that send you stuff from the internet. I don't know where I'm coming from. Anyway, I'm not here today, as you well see, and so I'm going to be presenting this lesson from afar. This is the first time I've tried this. I hope it works. And if it does, maybe I'll make a lot of videos like this and have them online for your study purposes. Okay, so here we go. This is your first Pear Deck question. So the teacher should just pause it now and give everybody about a minute to answer. And when you're done, unpause it. Okay, so heat comes from the sun. Well, let's go to the next one first. Okay, once again, go ahead and pause. Wait for about a minute. Okay, now moving on to the last one. Okay, once more, go ahead and pause it. All right, so let's go to the back of this quiz now. Heat comes to the sun by a process of radiation. A high temperature source radiates relatively high frequency waves with short wavelengths. Number 1. Newton's law of cooling applies to objects that, well, both of these, warm and cool up. So number 3. Okay, now let's go into the lesson. We stopped last time talking about conduction, how heat can travel via contact from one object to another. This is going to be now convection. You guys have heard the word convection before. It's when, probably through a convection oven, right? A convection oven basically is the same as your oven. The only difference is that it turns on a fan. So what's the big deal then? Well, convection, it circulates heat just a wee bit differently. So the question that I have here is, what if when a hot object warms a substance near it like it does in conduction, right? So, you know, like in your oven, you've got these hot coils inside your oven. They're touching the air next to them. And the only way to heat the food is if the air next to the coils heats the air next to that air, and then that air heats the air next to that, and so on and so forth until eventually that air next to the food gets warm, and then that air has to transfer the heat into the food. And my goodness, it can be a snail's pace if you've ever tried to heat a burrito in the oven compared to what it takes to do it on a microwave, right? Well, convection says, why don't we just sort of nip that process in the bud, and after I heat up some air next to this warm object, I'm going to move it away, like move that hot air next to the thing I want to heat up. And in its place, cold stuff will rush in, and then we'll heat that cold stuff up, get it out of the way, bring another piece of cold stuff in, and just keep the stuff circulating so that the heater element's always next to something that's cold compared to it. And the hot stuff moves over to heat up the rest of the place. That's convection. Now, I've shown a little picture here of a classic convection current. This happens in the old radiator heating systems that you see in big cities like New York's got these radiators everywhere. What they do is they're warm, they heat up the air next to it. Well, that air rises, and as it rises, it actually cools off, comes over here, then drops down. But you know, as it rises up, it leaves a void, so this cold air that's down here will rush up and fill it. And then as this thing falls, it'll also push some air up. But then while it's sitting here, this hot air will drop down and hit it and push it back up, and you get these nice currents. And so the warm stuff is circulating, and you heat up the room faster that way. The same thing happens with boiling water that you see here. The water that is heated, you guys know from last time, hotter water is less dense, so it floats. And as it floats, the cold stuff drops and then is touching the metal, which is touching the flame. So in that process, convection currents allow the water to heat faster. And that's just naturally what happens. This convection currents, well, do you remember when we talked about Santa Barbara and the sails and how the air over the desert would warm up and rise and then the air over the ocean would sweep in? Now, I didn't tell you at the time, but that was really a convection current. You see, here's the sun. It's heating up. Well, the air over the town heats up, rises, cools off, but the air over the ocean comes over to where it can start heating up over the land. And then this air that already rose up will be cooling off again, and it'll drop down over the ocean, and the cycle repeats. But in the nighttime, the air over the water is warmer, so it rises. The air over the land cools, sweeps in to fill its place, and as the air circulates up, cools over, it'll come back down and fill up, and you get these currents. That's convection currents right there. It's responsible for those sea breezes that we talked about earlier. Now you might ask yourself, why does warm air rise? Well, because it expands. Now, things expand when they heat up, right? We get everything, all dimensions get bigger. The molecules jiggle and bounce each other further away. So as it expands, it becomes less dense, and that means that the weight of the air that air is displacing is greater than the weight of that hot air. So the buoyant force pushes it up. But the weird thing is that as it rises and expands, it actually starts to cool off. And why is that? I mean, I thought hot air was supposed to rise, so why does it cool as it expands and rises? Well, because as the particles expand, they recede from each other. They start moving away from each other. So they always have some velocity away from each other. That means when they collide, their relative speed versus each other is low. And when they bounce off each other, they actually slow down a lot. Here's a little picture of it. You know, you've got this slow moving particle, but it's moving from left to right. Then you've got this fast moving particle moving from left to right. But from the fast moving particle's perspective, this guy's not going, this guy, because he's moving away from him, they're not coming together as fast as he's moving from our perspective. So when they collide, you know, there's less of an energy transfer. Well, I should say when they collide, there's less. This guy doesn't speed up as much as if the gas weren't expanding. So yeah, he loses energy and he doesn't gain as much. So overall, the net effect is that everything starts cooling down. And yeah, so what you see here is slower particles equals lower temperature, right? And so here's an example of an expanding gas. You see how everything is moving away from each other. And that's why this expansion reduces temperature. Okay, we have our first Pear deck. So let's see. Okay, so here's your first Pear deck question. You can hold your fingers beside the candle flame without harm. You can hold your fingers next to the flame. But don't put those fingers above the flame. Why? Go ahead and discuss amongst yourselves, see if you can come up with an answer. And if my substitute teacher would just pause the video here and help lead a discussion, try to get down to the answer. We were just talking about convection, so it probably has something to do with that. Okay, pause the video and unpause it when you're ready. All right, so if you were thinking about convection currents, what happens to the air right above the flame? It's hot, or the air right next to the flame, all around the flame that's getting heated up inside this ball. Well, it's hot, so what does it do? It rises. So how does this flame then get more oxygen to burn? Well, the cold air from here sweeps in from the sides, and that's where your finger is. So there's no warm air that's touching your fingers. But if you put your fingers up here, you're right in the path of all that hot gas rising, and it's gonna burn you. Okay, so that's that. Switch back to our Prezi here. Okay, so that was convection. Let's talk a little bit about radiation here. So light, just by its nature, is energy. It's little packets of energy just zipping across the cosmos, okay? And there's all kinds of different light. There's radio waves. You might think of radio as more sound. No, but it's They're waves of energy coming in via light, actually. There's infrared waves. Think of these sometimes as heat waves. And then, of course, light waves that allow us to see. Now, if you're sitting like this old man next to a fire, what are you, based on the last Pear Deck question, how you can hold your fingers next to a flame, how are you being heated by that fire? Are you being heated by conduction or convection? No, 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 no. Because that hot air is going to rise up the chimney stack. Besides, you wouldn't want that hot air anyway. It's way too hot. But the radiation, the light coming from that hitting you is enough. So you're just being heated by the lower form radiation. You don't want to be heated the other ways. So this radio waves appears all over there in space. So here's the Cygnus elliptical galaxy. It's one of those round, shapeless galaxies that are out there. This is what it looks like in optical light. It's light that we can see. But if we were to go to radio light, it looks very different. You get these big jets of gas coming out from it right there. And it's cold gas. And I'll tell you why in a second. You see that little bright dot in the middle? That, my friends, is a black hole. Pretty neat, huh? And that's just from seeing the different kinds of light. We don't see radio light, which is good because then it would be strange when we're listening to the radio in our cars. But we have instruments that can see it, and when they do, they reveal some startling things. Here's infrared light. So planets mostly radiate in the infrared light. You see that stars are mostly in the optical range, which is good. That's why the sun lights our planet. Gases and solids that aren't really alive, they tend to be in the radio. And then things that are warmed by a sun, like a planet and things in our everyday experience, they will radiate in infrared. This is Jupiter in infrared light. It's glowing. And this is people glowing in infrared light. And this is why a infrared thermometer works. What is an infrared thermometer doing? Well, simply it's looking for infrared light, and based on the intensity of the light, like look right here, this girl's face is pretty intense compared to this dude right here. This dude's got a stash too that doesn't look very warm compared to his face, right? Well, what this thing does is it looks at the light that's hitting it, and it just knows based on the intensity and the frequency what that temperature is. It's pretty wild. So that's how an infrared thermometer works. And that's how we actually know how hot things are out there in space. It's pretty neat, but this is a blue star, this is a yellow star, and a red star. And the question, and we know that blue stars are hotter than yellow, which are hotter than red, but why do we know that? Well, if you look at all the light coming in, this is what scientists do. If you look at all the light coming in from a telescope, what you see is that the wavelengths of lights that you see are on this graph right here along the bottom. And the intensity, how strong that wavelength that we're receiving is up here. So wavelengths of 200 nanometers, 2000 nanometers, which would be 2 micrometers, which would be 2,000th of a millimeter, pretty small, right? We're not getting very much power at these frequencies over here. There's not very much of that light hitting us, or it's not. What is hitting us? Well, it's just not very much, so it's not as intense. But as we start getting over here toward the 1 micrometer or half a micrometer, we start to get some pretty intense energies. And this curve here will tell you all the light that things are emitting. And when these lines start to break into the optical range, which is between about 200, 300, and 900 nanometers, that's when we start to see stuff. Anything beyond over here, this is the infrared line. This is the infrared range over here, and then we get microwaves, and out over here is radio waves. But it's not until this curve that's coming from how intense these frequencies are reaches into the optical range that we see things. And this curve actually right here corresponds to a blue star. And how do I know that? Well, look at the peak. Look where the most amount of light frequencies are coming at. It's coming in the blue range, which is why we see it predominantly a blue. This yellow star, we would see their peak. Look, it's mostly here in the yellow range. Okay, and that's why we see it mostly yellow. And then a red star, its peak is over here. Now you notice the overall intensity is much lower too for these stars. So man, these stars out here, they're just putting out so much energy, it's nuts. But just looking at these here and knowing their color, there's a really smart guy known as Mr. Planck. You guys may know him from chemistry, but he came up with a relationship that said, okay, based on where the peak frequency is, like this curve, the peak frequency is about 500 nanometers. This curve, the peak frequency is about 600. And this curve, the peak frequency is like about, oh, we'll say 700 or something like that. And he said, based on the frequency of the peak energy, the frequency that's putting out the most energy, that peak corresponds to only a specific temperature of an object. Isn't that wild? Only an object with a certain temperature would have a peak that looks like this. And so we've now matched it, where this is a 6,000 Kelvin curve. So anything with this curve is 6,000 kelvins hot. And anything with this curve is 5,000 kelvins hot. And anything with this curve is 4,000 kelvins hot. And anything with this curve, so hot. And the relationship from the peak frequency to the actual temperature is this nastiness right here. So I don't want to hear you guys complaining about my math formulas anymore, because I could throw this at you, okay? But that's how we know how hot things are in space, just based on their color and the frequency that we're getting from there. And it's all just radiated heat. That's radiated heat that's coming out. Now, how does radiated heat actually heat things up? Well, here we go. We have this lovely British countryside here, and we put a book outside. Well, this book is radiating because it has a certain temperature, and so based on its temperature, it's going to have some sort of black body radiation over here is what they call this curve, okay? Anyway, so it's going to be emitting some light, and it's actually in the infrared, but it's receiving all this optical light from the sun, which is so yeah, it's radiating, look here, it's radiating some infrared light, okay? But the optical light from that sun is way bigger, so the net result is that it's increasing in energy. Of course, as it increases in energy, it's going to radiate more and more of this. And eventually, they will reach equilibrium. Now, the book won't burn up because of the way it's losing energy through conduction to the heat, through the ground, to the air. It's going to gain energy a certain way. But the hotter it gets, the bigger these arrows are going to get, and eventually it'll reach equilibrium and it'll stay at that temperature. This is why your car gets hot when it's left out in the sun, right? Even in the wintertime, because it's receiving more light than it's radiating out. Now, let's say you take that same book back into your posh luxury office. This is a picture from my own office at home, actually. No, it's not, but I wish, right? And inside here, let's say we took that heated up book and we brought it in here. Now, the amount of radiation that it's receiving inside the room is low because it's just taking in the heat radiating from the objects in here, the infrared light. But it's radiating out all that extra heat sunlight that it was receiving, so it's hot. But of course, the net result here though is that it's losing temperature. It's losing energy because it's not taking in as much as it's losing, and eventually, as it loses temperature, these radiation lines go down and it'll reach again thermal equilibrium. So that's how radiation heats stuff up. Okay, so phases of matter. Oh, yeah, so before we do that, I want to make sure that we are doing some more Pear Deck quizzes, okay? Okay, so here's our next Pear Deck quiz question, and this question is going to be using our thermal equilibrium processes, okay? So we're mixing 10 kilograms of 90 degrees Celsius water with 30 grams of 20 degrees Celsius water, and we want to know what will the final temperature be. Now, for this, you're going to have to use that equation, okay? The equation is Q equals mc delta T, but we recognize that a hot object is going to be losing, so negative Q, so that's our outflow of heat, and the cold object is going to be gaining, so it's a positive Q in. Now, If you guys already did this problem, because I know one period did, and you've already done this equation, feel free to skip ahead until you see the next paired equation question. Okay, so this MC delta T is going to have a negative, right? And this one will be an MC delta T positive. So this becomes negative MC temperature final minus temperature initial, because it's a difference. And we're going to get positive MC temperature final minus temperature initial. Now the negative distributes into here, and that changes this to MC temperature initial minus temperature final. And that will equal MC temperature final minus temperature initial. Okay, and of course this side is the cold side, and this side is the hot side. Okay, so in this problem that you just saw, we're taking 10 kilograms of 90 degrees Celsius water, and we're putting it into 30 kilograms of 20 Celsius degree water, and we want to know what is temperature final. Now, we have to recognize here that the TF on both sides are going to be the same because they're going to reach thermal equilibrium. And so those are the same variables. And now you have all the information you need to do the others, except for if you recall that C for water is 4.184 joules per gram, not kilogram, Kelvin, which is the same size as a degree in Celsius. So we don't have to convert Celsius to Kelvin or anything like that. So now you have everything you need to know, right? That plugs in there, that's going to plug in there, this is going to plug in there, that goes in there, this also plugs in over there. So what does that mean? You can do algebraically, and then this plugs in there. And then just have to simplify it and get your answer. So what I want you to do now, you have the problem on your paired sheets. Just if the substitute would just pause the video and let everyone work it out and try it out, see if you can get an answer. Okay, are you ready? So you plug that in, and notice the C's cancel because they're the same on the other side. So all we have is M T initial minus T final equals M T final minus T initial. We can start to put numbers in. We're going to get 10 equals 90 minus T final equals 30 T final minus 20. Right now also we can cancel out these zeros, so we just get 90 minus TF equals 3 times TF. Well, let's just distribute it. So 3TF minus 60, okay, and we can just combine terms. This one goes there, that one goes there. We get 150 equals 4 temperature final. And so the temperature final will just be 150 over 4, which is 37.5 degrees Celsius. So that was closer to the 30 kilograms. So that makes sense. We're feeling pretty good about our number because it was closer to the larger amount of water. Okay, so now there's one more paired question regarding this. Hey, it didn't cut out the video. Maybe I can just switch down here. Oh, no. Okay, so there's a new one. A red hot 327 degrees Celsius 5 kilogram strip of copper is lowered into 18.9 kilograms of room temperature 20 C water. Copper has a C, that's that specific heat, of only 0.386 joules per gram Kelvin, and water is at 4.186. So what will be the final temperature once these two objects reach equilibrium? Oh no, we can't do our little trick of canceling out the C's this time. Well, that's no fun. So we have to include them, and it's going to get a little messier this time. Okay, so let's go over to the other problem. So go ahead and pause it again. You're going to use the same equation as last time. That MC T final, MC open parentheses T initial minus T final close parentheses equals MC open parentheses, T final minus T initial, close parentheses, where the first one is the hot object, the second one's the cold object. So go ahead and pause this video now and try to work this one out. Okay, so here we go. We're back in action. So we had the 5 kilograms, and the C was 0.384, right? Joules per gram Kelvin. And it was coming from, did I do that right? I'm afraid to go from one to the other because 327. Okay, so 327.386. Let's see. Yeah. Okay. So 323.86, and it's going from 327 to some final temperature, and that was equal to 18.9 kilograms of water, so 4.186. Oh, sometimes I use 4.186, sometimes I use 4.184. I don't even notice myself doing it, so you can use either one. You won't be docked on the test or anything like that. Okay, T final, this one is 20. Oh, we don't know T final here, do we? So T final minus that 20 degrees. Okay, so now you might say it's time to convert the units, and that would be fine if you did, but I also want you to notice that you have kilograms on both sides. So those kilograms actually just cancel out. You don't have to convert the units here. Isn't that weird? And the joules per gram Kelvin cancel out. So you don't have to convert those units either. It's kind of nice. So here we go. This is one time when it's not easier to solve it algebraically before you plug in numbers. So I'm just going to start doing 5 times 0.386, 1.93. So we get 1.93 times 327 minus T. I don't need to say T final anymore because I don't have any other T's. Okay, then 18.9 times 4.186. So we get 79.1. Okay, and that's going to equal T or just T minus 20. So we don't need the F anymore. There's only one T. Okay, so I gotta get T all by itself. So first things first, let's get rid of this 19.3 from both sides. Cancel, cancel. 79.1 divided by 19.3, and we get 4.10. So we're going to have 327 minus T equals 4.10 T minus 20. Let's distribute these out. So times 20 here, I'm going to get 82 basically. So we're going to have 327 minus T equals 4.1 T minus 82. It's kind of convenient. Okay, so let's bring these things back over now. So now we have 5.1 T. And over here, what's 327 plus 82? So we're going to get 409, right? Because 80 plus 320 is 400. 2 plus 7 is 9. Okay, so 409. Okay, and then we divide by 5.1. And we get that the T is equal to, let's see, 80. So it's only 81.1 degrees. So that 5 kilograms dropped into the almost 3 times as much water, even though it was way hotter, 327 degrees, because it doesn't take a lot of energy. It loses temperature fast for just a little bit of energy. It only drops 0.3 joules every time it drops a degree, and that's per gram, so just not very many joules coming off that thing. And it takes a ton to heat up water, so we expect that the final temperature would be nearer more to water, and sure enough, it's only 60 off of this guy, whereas it's 240 off of this guy. All right, so that's how you do those thermal equilibrium problems, okay? It's very important to be able to learn how to do for the upcoming exams. Um, there you go. Oh, it didn't drop my video. This is awesome. Okay, so there's the video. There's my presentation. Let's go full screen. All right, so now phases of matter. Um, Now, if the bell's about to ring, just go until the bell rings, and then we'll all just make a note of at what point in the video you guys stopped, and I'll just start from there next time. Okay, so phases of matter. So yeah, we see that things heat up and cool down, but we know that when things cool down, or actually heat up, like liquids, when they heat up, they evaporate liquid into gas. Or if a gas cools down, it condensates, or condensation, gas into a liquid. When a liquid goes into a solid, we freeze it, and when a solid goes to a liquid, it's melting. So we all know these terms. So we're not going to now dive deeper into these. And we're going to talk about, okay, the big question is, when something evaporates, that energy that it takes to take from one to the other, it's got to come from somewhere. It can't just be created out of nowhere, and it can't be destroyed. So like evaporation, when water evaporates, it's going from a liquid to a gas. That's a more energetic state, right? So if it's gaining the energy to turn into a gas, what's losing the energy so that water can gain the energy and evaporate? Well, it's generally whatever's left behind. So for instance, look at this guy with this canteen, okay? So his canteen here, um, you want to keep that water cool, so you soak the cloth on the outside of it. Why do you do that? Well, the soaked cloth will hold a bunch of water, but that water will eventually evaporate. And as it's evaporating, it has to be gaining energy to do so. So if it's gaining energy by going to evaporation, where's it getting it? Well, from the canteen. And where's the canteen getting it? From the water. And that's why the water is cold inside when you wet it like this. Pigs have to do the same thing, and elephants actually too, a lot of animals, because they don't have sweat glands. So how do they cool down? Well, they coat themselves in water, knowing that when that water evaporates, it's got to draw energy from something. And since water pulls a ton of energy, as it evaporates, it cools that pig down pretty good. This will explain also why you're so cold when you get out of the pool, because you're covered in water and that water's drying off, evaporating. Now, where's it getting that energy? You. And that's why you feel that as it evaporates, it's just being frigid. Ugh. Okay. Now, condensation is the opposite. So if water takes energy when it goes from water to gas, what's it doing when it goes from from gas to liquid? Well, it's got to be dumping energy, right? And so what happens to that energy that it dumps? Well, whatever it condenses on gains the energy. Okay? So these radiators, we talked a little bit about these earlier, but these are the classic radiators that you see in old buildings. How are they warming stuff up? Well, what happens is hot steam gets pumped up into the inside of these radiators, and as they're in there, well, they cool off, and as they cool off, well, they start to become water again. And where does that energy go? Into the pipes of the radiator. And what does the radiator do with it? Well, the air around the radiator is cooler than it, so it dumps the energy into that air, starting those convection cycles that we talked about. So, you may have noticed that when you're taking a shower, at first you're kind of cold when you're in that water, um, until there's enough steam in the shower. And why is that? Well, so you've got water on you that's trying to evaporate, draining you of heat. But it's so steamy in there, there's so much moisture in the air, the air can't take it all. And so a lot of that water will condense out. And where does it condense onto? You. And so it gives you that energy back that you're taking out. So when you're comfortable in the shower, and this goes for right after the shower's off, you turn off the shower and you're inside your little cocoon of steamed air. And so you're warm because you just as much, even though you're wet, because there's just as much energy leaving you through evaporation as there is hitting you at condensation. Now, of course, once you step outside the shower, that air doesn't have enough moisture to replace the energy that you're losing to evaporation. with condensation. So it's cold, right? Um, Now, if anybody has a question, feel free to pause the video and just rewind if you want to hear me say it again. Okay, so boiling. So once again, we're just trying to follow the heat to find, what cools down and what heats up. So when you boil something, what you're doing is you're taking some water at the bottom of the pan and you're making it really energetic, so energetic that it actually wants to start knocking its neighbors away and creating void pockets and becoming vapor. Well, what keeps it from boiling is you've got the atmosphere pressing down on top and all the water pressure from the water on top. But eventually enough water is moving, and it's moving fast enough that it's actually going to push back the water on top and the atmosphere on top and become a water vapor pocket. Rise to the top because it's less dense and boil away. Okay, so if this water here is high energy though, when it leaves, where did the energy that went into it come from? Well, it's the air around it. So when it comes up and leaves, it takes that energy with it, doesn't it? And what does it leave behind? Cold, sad water that has to heat up over here, just like before, then form another water vapor bubble, and then as it leaves, it takes that energy with it. So actually boiling, believe it or not, is a cooling process because it gets rid of the hot stuff, leaving the colder stuff behind. And this is actually why water stays at 100 degrees when it's boiling. Because at that point, enough stuff is leaving, taking its energy with it, that it matches the amount of energy coming into the water, that it matches the rest of the water, right? So it just stays at that 100 degrees. Or if you're higher in altitude, it'll boil sooner because at that point there's less air pressure. So this water stuff will push away. So that's, here in Utah, water doesn't boil at 100. It actually probably boils more like 98 or 97 or maybe even 96. I have to look it up to know the exact number, but that's boiling. So yeah, actually things cool down. Isn't that weird? So freezing, of course, if things freeze, they are releasing energy into the wild around it. So as they get colder and then lock into a solid, they are sending energy elsewhere. So a trick that old farmers used to have back in the day when they were worried about a frost overnight and they were trying to protect things out in their barn or crops in a greenhouse or something, and they were worried about them freezing over in the uninsulated rooms. They could actually go out and just leave a bunch of buckets around the room of water, full of water, knowing that as the air tried to cool down in there, they would also have to cool down, or as the building was losing heat, if it wanted to keep losing heat, it also had to draw heat out of that water. So that it had to, before it could freeze, it had to freeze those buckets of water. Well, that takes a lot of energy, and it's not likely to happen, so you would avoid a frost inside just because of the presence of buckets of water. Kind of wild. Now, one note here at the bottom is the temperature at which things are gas, liquid, or solid. It also depends upon outside forces. Because remember, things boil depending on how much pressure's on them. So what if there was so much pressure that the water couldn't boil, leave it at 100 C? Well, then it would boil at 104 or 105 C. This is the secret behind pressure cookers, actually. You seal the chamber, and as the water boils, it creates this really high pressure gas above, which increases the boiling temperature of the water. And therefore, you're able to cook stuff faster because the water is actually hotter than 100 degrees C. Kind of neat. But you could have so much pressure that things would not even boil at a certain temperature. In fact, they would melt at their normal temperature. And a good example of this is the sun, the Earth, the inside of the Earth. We know that we got this rigid outer crust, and then we've got some thicker rock that's sort of plastic, sort of liquid. And as we get down to the heavier stuff, the iron, which is heavier than this stuff, so it sinks down to the center of the Earth. This iron is super hot, like 6,000 degrees, 5,000 degrees. That's like the temperature of the inside of the sun, which means that's why it's aptly glowing here. But look at this. It's solid. The inner core is solid. How could anything be solid at 6,000 degrees? Well, it's holding up the whole pressure of the entire Earth. So it takes way more heat before it can liquefy. Now out here, there's not as much pressure, so this stuff is able to liquefy, but not this stuff. This thing has a huge pressure on it all the time, and that's why it actually stays solid. Okay. Now, you might have another question. How much energy is required to get from one phase to the next? Because we know how much energy it would take to get water from, say, 10 degrees Celsius to 100 degrees Celsius. We just do the MCAT, MC delta T. Mass of the water, 4.186 for water, C, then 90 degrees change from 10 to 100. And we would know exactly how much energy has to be put in order to bring that water up. But what about melting or vaporizing it? Well, the interesting thing is as you take ice, melt, and bring it up to 0 degrees, so it'll start melting, you find that because the water that's melting off takes energy with it, that ice stays at 0 degrees. The solid stuff stays because the liquefying stuff takes energy with it, leaving cold ice below. So it stops at that 0 degrees. It doesn't actually, the ice stays at 0 degrees. And the water stays at 0 degrees too, actually. Because even though it's gained energy to become liquid, it's still pretty cold, and it can't really gain any more energy because it's in contact with all this other ice. So it stays at 0 too. So you get this plateau where you're pumping energy into it, but the temperature ain't rising. And it's not going to rise until all that ice is melted into water. And then you can MCAT it once again. So you can MCAT here. So in the ice has a certain C, it's 2 joules per gram Kelvin, 2. If the substitute wants to go write that down, just say C ice equals 2 joules per gram Kelvin. But once it hits this melting point, then you have to dump in actually a ton of energy. This down here says 80 calories, which is 335 joules for every gram. Hey, that's way more than ice was, wasn't it? It was 2 per gram for ice. But then here it's 335 joules per gram. That's true. And notice I'm not saying joules per gram Kelvin for these numbers because they stay at the same temperature, so it doesn't make sense to include per degree in there. So when you're dealing with the C, because there's a C for this stuff, that's specific heat. There's a C for just this stuff where it's just changing phase. And that's just, it doesn't have any sort of degree in it. And once we're all melted, then we can start doing MC delta T again, where C is now 4.186 to bring the water up to 100. But once we hit 100, once again, that water's boiling off, taking energy with it. So it keeps the water that's left at 100. And until you boil off all the water, the steam won't heat up anymore. And look how much energy you've got to put in to vaporize water. It's ridiculous. 540 calories. We only had 80 over here. Now it's going to take 540 calories to evaporate 1 gram of water. And yes, that's true. And that 540 calories actually converts to 2,260 joules per gram of water vaporizing. So it takes a ton of energy to vaporize water. Tons. And this actually leads to a big problem with steam burns, because if you have to heat things up to go this way on the track, if you want to cool things down, let's say we want to freeze some steam, well, we've got to draw out 540 joules per gram or 540 calories, or 2,260 joules per gram of energy from the steam before it becomes water. Then we've got to pull out 100 joules for every gram, and all the way down to ice. Then we've got to put another 80 per gram. Oh, geez, just to freeze it. So that's how much energy we're taking out, and then you're back to ice, right? So a steam burn is way worse than a liquid boiling water burn. And the reason for it is when you get hit with that steam, for it to come into thermal equilibrium with you, it's got to convert from steam into liquid water. And that means, and remember what happens on condensation. Where does the energy go when it goes from evaporation to condensation? It has to go into the thing that it's condensing against. and that's U. So it's dumping 540 calories, or 2,260 joules for every gram of steam that's going into water. Well, that's enough joules to really hurt your cellular structure and burn you. So steam burns are way worse than just hot liquid burns. Okay. So let's see, are we done at this point with the paradigm? Yeah, so the Prezi is done, and now we just want to convert over to do our last Pear Deck problems. Okay, how do I get the Pear Deck? I have to close this. Didn't drop my connection, that's great. Okay, so back to here, okay. We did that Pear Deck question, didn't we? What am I looking for? Oh, it's down here. Okay, so we did this one, we did this one. Okay, so here's the question, and I'm afraid that if I make it full screen, my recording will stop on me. So I just want to see, how much energy would it take to melt 100 grams of negative 20 degrees Celsius ice? So remember that this L right here, you know, we use C for the MCAT portion, right? But when we're transferring between phases, we use L, not C. And this is just L sub F. That's supposed to be a subscript F. I can't do that in Pear Deck, unfortunately. But what it means is the heat of fusion. It means how many joules do I have to do to transfer from liquid to solid, or vice versa. So remember, that's 80 calories per gram Kelvin, or 335 joules per gram Kelvin. So if you've got 100 grams, and it's got to go first, it's got to change 20 degrees using the MCAT equation, using the C for ice, which is 2 joules per gram Kelvin. Okay, and once you've got 100 grams of it up to 0, then if you're going to melt it, you've got to put 335 joules, or 80 calories per gram, to get it to liquid. Okay, so you're just going to add up those two heats. You know, you've got the MC delta T and then just the M times L. So you just sum those up. Okay, so pause the video and give it a shot. Okay, so I hope you've had a chance to discuss. Okay, so if we wanted to do this, we want to know how much energy does it take to melt the 100 grams of ice. So we have our MC delta T, because we know it's negative 20 degrees. But we're going to have to melt it, so I'm going to have to add in my ml of fusion. So I'm going to get my 100 grams and my 2 joules per gram per Kelvin. And then it's going to change 20 degrees, isn't it? Because it's going to from negative 20 to 0. I might say, you know, my final temperature is 0, so I'll take my difference, which is negative 20. So I'll just end up with a 20 in there, right? So then I'll add in here, once again, 100 grams. Let's keep our units in here. And then it's just going to be 335 joules per gram. I don't need kelvins in there because it's all staying the same temperature. So the grams cancel, the kelvins cancel, the grams cancel, and I'm left with nothing but joules. That's good, because that's what I want to know, energy. So we just now plug and chug. So we're going to get 100 times 2, which is 200, times 20, plus 100 times 335, 37,500. That's a lot of energy. And you notice that the melting part of it was more by far. Look, this was only 4,000 joules. This was 33,500 joules. That's a lot more. Okay, so that's our answer right there. Okay, so let's try another one. This one down here. This one's a little bit trickier. So how much energy would it take to boil 100 grams of positive 20 degrees Celsius water? Just remember that the L of vaporization, that L sub V, is 540 or 220. Go ahead and pause again. Okay, I hope you've got a conversion on an answer. Let's try this. So here we go. We've got that the Q is going to be MC delta T plus M L sub V. And what do you expect? You expect this to be a big number or a small number when compared to this one? Well, the L sub V is bigger than L sub F, so you should expect that this term here is just going to dominate the value of Q. But we'll add an MCAT nonetheless. So we've got 100 grams, the 4.186 joules per gram Kelvin, and so we're going from 20 degrees to 100 degrees. So I've got 100 minus 20, that's a 0. And that's going to equal, plus 100 times 2260 joules per gram. This is gram. You can come in, anyway, never mind. So the grams cancel, the kelvins cancel, grams cancel, cancel. So all we're left with is joules, which is great. So we're going to have now 100 times 4.186 times 80, because that's the difference between 20 and 100, right? So 80, so that's 33,488. It's not bad. It's a lot of energy. Let's see what happens when we get over here. We're going to have 22,600. Oh, wait a minute. I think I did something wrong. Oh, 000. Okay, that makes sense. Okay, so now, just as we thought, this term is huge. Huge. It's huge. It's got to be huge. Sorry, Donald Trump came around then. Okay, so here we go. So 33488 plus 22,600, and we get 259,488. These are just ginormous numbers. Wow. Or joules are nothing. Well, it's both actually. They're huge numbers and they're nothing. But now you can see why food is reported in calories, capital C, kilocalories, because these numbers are just bonkers, and that's only to take 100 grams of water up 80 degrees. You know, it's not that crazy of a process. And if I divide by 4.186, I see that this is almost 62,000 calories. Good heavens. Do you want to see your food with numbers that big? I mean, but that's what they would be. That's actually really low calories as far as food goes, right? But you can see how much energy it takes just to heat up your body, like to keep your body at a temperature when you're mostly water. It takes a lot of energy, and that, I mean, hundreds of thousands of joules. And because it's just hundreds of thousands of them, it's just so unwieldy. That's why we shave off the 3's and call them kilocalories or capital C calories. And everyone feels a lot better. All right, so those are phase shifts. Those math is going to be some of the things that you're going to be doing on the upcoming test, so you're going to want to be familiar with that. If there's still time, the substitute could rewind this and you could try different problems, or just write your own and attempt them. You know, maybe try to take some ice from -50 all the way up to like 150 degrees steam. You'd need to know the C for steam, and I don't remember that. You could Google it, I think. Anyway, but that concludes chapter 16. Believe it or not, we've already done 15 and 16. I don't know if you got to the end of this video in class, but if you did, we only have one more chapter left, and then it's review and on to the test. So it's going quick. Now, homework. The homework is posted on Veracross, and it will be due Thursday for 14 and 15. That's a combined homework assignment. We're going to have a 16 and 17 combined due on the day of the test next week, which is probably going to have to be Tuesday so that we can review it on Wednesday, because we don't have school next Friday because of in-service. So that's coming up, and hope you enjoyed this lesson on thermo, and we'll see you later.